like the first value, the R1, right? Now, in case 2, this was, so in case 2, let me just, what I'm going to do is, let me do something here first, right? Look at what you get, the Cn. If I solve this equation for Cn, what do we get? You get a minus, right? Then you move this to n plus r minus 1. And then you divide by these two combined, so this gives you 2. This time solving isolating Cn here to get this. Okay. And now let's plug this value here for r. So r equal to 2, you get 2 here. This is 2. So n plus 2 minus 1 is n plus 1, right? This is n plus 1. Now, if I multiply this and I subtract the 2's cancel and you get what? N squared plus 3n, right? And if you factor that, this simplifies to be what? N times n plus 3. Okay. And now we start computing the C's. This for the first power series. So C0 is C0. C1, you get it here when you make n equal to 1. What do you get? Minus. If I plug 1 here, what do you get? 2 over 1 times 4 times C0. So what is this really equal if you simplify? Minus 1/2 C0. Let's go to the next one, C2. If I plug n equal to 2 here, what do you get? 2 plus 1, 3 with a minus. And if I plug n equal to 2, you get 5 plus times 2, 10 times C1. But C1 is minus, so you plug minus 3 over 10 times, and you plug what C1 is in terms of C0, minus 1/2 C0, and you combine these two and you get minus minus plus 3 over 20 times C0. So, and then you can keep on going computing, right? So let me plug those numbers here. So you get C0 x to the 0 plus R1, R1 is 2, so times x squared. The next term will be the C1, which is minus 1/2 C0 x cubed. Then plus the C2, but the C2 is 3 over 20 C0 x to the 4, etc., right? Plus. Now look at what happened. In all these terms, they have a common factor C0 and an x squared, right? So let's factor that, and what do you get? 1 minus, here you get the 1/2, here you get, this is x, and the x squared. So this is the first power series solution, the one for the R1 equal to 2. And now we move on to the second one, right? And on the second one, in case 2, we're going to first assume that we don't have this. So let me just compute the other coefficient. So here, I'm going to assume that this is now, and the R2 is now equal to -1, right? So what I'm going to do is I'm going to go here, what I had before, the general one, with it. This one was n plus r times n plus r minus 1 minus 2. And these are for the tildes, right? Because I'm going to use the R2, the -1. So I'm going to put -1 here for R. So -1 minus 1 is -2. So you get this is -1 minus 1 is -2. And if you do the algebra, you expand these two and subtract 2, what do you get? N squared minus 3n, so you get something similar to we get before is n, this denominator. This denominator is n times minus 3. For the coefficients of the second power series, the y2. And now we start computing some of them. Let's do it here, right? The C1, the C0 tilde is the yesterday. The C1 tilde, if we use that, what do we get? If I plug n equal to 1 there, you get minus. You get minus, if n equal to 1 minus 2 is -1 here on the top. And on the bottom you get 1 times -2. So minus minus plus, so you get let's go to the next situation. Then what do you get when you plug n equal to 2? What do you get when you plug n equal to 2? You get 0. And then, once that's 0, if we keep plugging on the recursive formula, all the remaining ones are 0. The C3 tilde, 0, the C4 tilde is 0, all. So the only ones that they are not 0 are these two. So, let me plug them here. What do we get? Remember, R2 is -1, so let's put -1. The n equal to 0 term, when you make n equal to 0, you get C0 tilde, x to the -1, which is 1 over x, plus C1 tilde, that's the only, which is, according to this, -1/2 C0 tilde times, when you make n equal to 1, you get the constant, nothing more, right? And then the remaining ones are 0. So let me factor the C0 here, C0 tilde, you get 1 over x, now, obviously, we at here is independent from this. So these two, the assumption we make on case 2 that the constant with the logarithm was 0 is really 0, and you get two linearly independent things. This power series and this function, really this function. So this is telling us is that this function, as a simple function, 1 over x minus 1/2, is a solution to the original. And it is, you can check, make the constant C0 tilde 1, and you can check that this is a solution of this. Plug this here for y, y2. Take a derivative and plug it here. Take another derivative and plug it here, and you will see that the left-hand side works out to be 0. It's simple, right? What is the first derivative? Constant -1 over x squared. What's the second, the next derivative? Second. Plus 2 over x cubed. Now, let me plug those things here, right? So what do you get? X squared times the second derivative is 2 over x cubed plus x squared times the first derivative, which is that, minus 1 over x squared, right? And minus 2 times the function, the whole function. 1 over x minus 1. Let's do the algebra here, right? Look, x squared over it, so it gives you these two. Now in the second term, the x squares cancel, right? And you get just a minus 1. This whole thing is minus 1. So plus minus minus. And now distribute this, right? So you get minus 2 over x plus 1. And look at what happened. 2 over x minus 2 over x minus 1 plus 1.
C4 over there, once you get 0, you just forget on the tilde, is it? The procedure, once you get a 0, you just forget.
Once you get 0, because once one of the c's is 0, the next one is a number times the previous.
Okay.
But if that's 0, that's going to be 0, and then from then on, all of them are 0 because of the recursive formula. The next, in terms of the prime, multiplies, but that's 0. So 0, 0, 0, 0, 0.
Another question, on all three cases, can you just plug it into the original equation and check if you did it right? Well, when you got a solution, right?
Well, I mean, if you get a function, if
Yeah, but we couldn't plug in the first
yeah,
one.
in this case it's simple because you only get this function and you could do what we just did up there.
Yeah.
But in the case of the y1, it's a whole power series.
Okay.
So it's gonna check that this is a solution. It is more time consuming.
Yeah.
So you just, we know we did everything okay. So this is. So what would be the final answer to this problem? What is the general solution of this?
It's C0 times the y1 linear combination.
Is this right? Let's put it with the C0 times all these power series, right? In the bracket 1 minus 1/2 x plus 3 over 20, and you can stop here, right? You can in there. Plus, and another constant c 0 tilde if you want, times the one we get. That's the solution. Where these are playing the roles of the C1 and C2. They are constant, whether you call it C1, C2, or C0, C0 tilde, they're just constants. So that will be the final answer, the one up there. Right? Constant times this whole thing, which would be the y1, plus another constant, the C0 tilde times the y2. That's all the solutions, all the real solutions of the original. Right? About point, which is, we checked that on Wednesday, a regular singular, in this case too. Now, let me just mention something, right? Once we get these roots, it was case 2. In the test, if in the test there is a problem, there would be a problem, power series solutions from this chapter 6. If it's a regular singular point, and it could be, and this is what we call the method of Frobenius, to find the two linearly independent power series in that case of a regular singular point. In the test, I cannot give you a case 3 because that's gonna take forever. So in the test there will be a Frobenius case, regular singular point. But you are not going to have, the first is okay, but for the second one, there won't be a logarithm. It will be, so in terms of complication, this is the most complicated thing I can give you in the test, the one we just did. So here you have a very
You've got it on video.
clear illustration. It would be like